So after the session 7, session 7. So I recall the definitions. What is subfield? Subfield. We already explained in the subfield the subring ideals. The same way we are explaining the subfield. What is the subfield? So you know the definitions of a field. I recall the field as a commutative, as a unity, each non-zero element as a multiplicative, inverse. The same field taking K is a subfield of K, subfield of F. Let F be a field. A non-empty subset K of a set F is called a subfield of F. If K is closed with respect to operation of addition and multiplication in F, and K itself is field for those operations. See, K is closed with respect to operation of addition and multiplication in F. But what is the K is closed with respect to operation of addition and multiplications? We already know the definition of subring, ideals, subring, ideals. So, A belongs to K, B belongs to K, then A belongs to K, B belongs to K, A belongs to K, minus B belongs to K, A plus of minus B belongs to K. So in the case of subring, ideal, subring. So A plus of minus B means A minus B. A minus B belongs to K. So if we take elements, there are the necessary and sufficient conditions for non-empty subset K of a field F to be a field of F are A belongs to K, B belongs to K, then B belongs to K minus B belongs to K, A plus of minus B belongs to K, that is A minus B belongs to K. This one conditions in a case it is closed under additions. So in closed under multiplications, say A belongs to K, a non-zero element B belongs to K. If a B belongs to K, if a B exists, suddenly 1 by B belongs to K because it's a field. Each non-zero element has a multiplicative inverse. A is there, A not equal to 0, suddenly 1 by A. That is a field. So B not equal to 0, suddenly 1 by B exists. Alright. A belongs to K. A non-zero element B belongs to K. Suddenly 1 by B belongs to K. A into 1 by B belongs to K. That is a field. So this must be in a subfield form. This is the must. See, the necessary and sufficient condition for non-empty subset K of a field F to be a subfield of F are A belongs to K, B belongs to K. This implies A plus of minus B belongs to K. That is A minus B belongs to K. Second, A belongs to K, a non-zero element B belongs to K. That implies A into 1 by B belongs to K. This is a necessary and sufficient condition for the subfield. See, the example be familiar about the third in the I explained in the session 1 2 session 2. See, set of all natural numbers certainly contains set of all integer. Set of all integer certainly subset of set of all rational. Set of all rational contains certainly subset of real. Set of real certainly contains set of all complex. Certainly. So in the field, this case is a field. So larger field is N is a smaller field. So the field of rational certainly is subfield of real numbers. The field of real numbers certainly a field of complex number. Certainly a subset of complex number. So complex is an extension field. So what field does what condition does not is certainly complex is word. So suppose A is a subfield of field F. Now A is a group with respect to additions. Therefore D belongs to K. This implies minus B belongs to K. So if you take A, B, that's field. So if you come to the right side, it's a plus sign. If you come to the negative, is the left side is there. So that's all. If you take whatever may be there. So rational we define. So we go for right side, we get. So if you come to the left side, this also an element belongs to that field. Whatever may be the rational, the integer, whatever in phase of complex. If you think about in the right hand side, it's a positive we get. If you think about in the left side, we get the negatives. That's why if a B belongs to K, minus B belongs to K. Also, K is closed with respect to additions. For example, if it am already given the, if A belongs to K, B belongs to K. So B belongs to K, suddenly minus B is also in K. So A plus of minus B belongs to K. That is A minus B belongs to K. Thus it is similarly in the form of a subring form. Subring. So subring is in form A is there, B is there, minus B is there, A plus of minus B form. Now each non-zero element of K possesses a multiplicative inverses. Therefore, non-zero element B, suddenly B inverse in exist. This is one way you are saying. But you come to the multiplications, if K is closed with respect to multiplications, A belongs to K, a non-zero element B belongs to K, the product A into B inverse belongs to K. This is a addition and multiplication is necessary and sufficient condition here. Hence, the conditions are necessary. If you come to the sufficient, what's the necessary? A is there, B is there, non-zero element is there, inverse is exists, suddenly product is in X. If you come to the sufficient, the conditions are sufficient. Suppose K is non-empty, subset of F, the condition 1 and 2 are satisfied. As we have proved as subring, we can prove with the help of conditions K and additions is abelian. Abelian is same as commutative group. Abelian group is a commutative group. A plus B equal to plus A. Now, let be an element, a non-zero element of K. The form 2 we have A belongs to K, a non-zero element A belongs to K, then A inverse belongs to K. What's A inverse? Is 1. It belongs to K. Now, is 1 belongs to K means unit element in the subfield. Unit element as in the subfield. Therefore, again, the 2, 1 belongs to K, non-zero element A belongs to K, 1 into A inverse belongs to K. This is a unit element in a subfield. Unit element in a subfield. Also inverse in subfield. Unit element and inverses. So, the A 1 belongs to K and A inverse belongs to K. Therefore, each non-zero element of K possesses a multiplicative inverse. This is one way you are define in the subfield have an inverse and the unit elements. Is enough. Yeah, any field have an inverse and unity. Then suddenly you can use a field form. So field as a field form. Now let A belongs to K, a non-zero element B belongs to K, then suddenly B inverse in K. This way A belongs to K, B inverse K, A of B inverse of inverses. A of B inverse of inverses belongs to K. What is a B inverse of inverse? Is a B itself. B inverse of B inverses. So B itself. So AB belongs to K. Also B equals 0, then AB equals 0. 0 belongs to K. See, observe, unit 0 element it also belongs to K. Therefore, the product AB belongs to K. For all A comma B belongs to K. So similarly, we come to the associative multiplication distributive multiplications over additions must hold in K. So this is a primary additive inverse commutative as a unity is everything in the subfield form. We come to the associativity. Associativity A of BC equal to AB of C. So associativity under multiplication. We come to the distributive A of B plus C equal to AB plus AC. This is distributive under multiplication. We come addition must hold in K since they hold in F. What hold in K? Suddenly hold in F. What hold in F? Suddenly. Hence, K is a subfield of F. For example, the field of real number is a subfield of field of complex number. The field of rational number suddenly is a subfield of field of real number. This is already I'm repeating this type of examples. Why? This is complex is a larger field. That is why I am saying the real is suddenly a subset of complex. The rational suddenly is a subset of reals. The set of all integers suddenly subset of rationals. This is where we go for extensions. The extensions we feel this suddenly word. This is a strong result. The strong examples for subfield. So next session, I am going to prove a subfield theorem. Some simple we are using necessary and sufficient conditions now. Using that necessary and sufficient condition, what needed? We are using the statement form. I explain in the what's the conditions word associativity, existence of identity, existence of inverse, existence of distributive, right distributive and left distributive.